Assalamu alaikum. Welcome to lecture 12 of natural language processing. So today we will continue our discussion on classifiers or text classifiers, and we had already discussed naive Bayes. We discussed logistic regression last time, and we will extend this further today to neural networks. And along the way, we'll also discuss some properties of naive-Bayes logistic regression and neural networks, and maybe their application to sentiment classification. So that is basically the agenda for today. We don't have a quiz today, as I think discussed last time. So we'll start our quiz sequence from next week or maybe the following week. So we do have an exam at the end of this week, and the midterm exam at 1 p.m. on Saturday. And on Thursday, I'm not too sure, maybe we can have a review session. But if we want to have a review session, then I would like to have more participation. Otherwise, there's no point in having a review session. So it's all up to you. And of course, the content for the midterm exam would include today's lecture. So we will not include Thursday's lecture in the midterm exam. So any questions? Any questions, comments? So let me start with binary logistic regression. And the model for the binary logistic regression is given by y is equal to the sigmoid function of, you can say, a. And let me write out the sigmoid function 1 divided by 1 plus exp minus a. And a is often, a is taken as a linear model of features. So a is basically W transpose. W is a vector, weight vector of, and basically that's, we have the inner product with the feature vector x. So of course, A is a scalar. So you have an inner product occurring here, a vector multiplying with another vector, inner product to give you a scalar. So in general, these, if you write out this expression, it's basically W naught or W0 plus W1 x plus W2 x2 plus W m x m. All right. So this is what A is, which is a linear model in terms of the feature. And what are the features? The features are x1 to xm. And W naught is often called a bias term. If you think about a straight line, this W naught basically shifts the line. Or in general, if this is a hyperplane, it shifts the hyperplane. So it's kind of a bias that shifts the hyperplane. Of course, all the other uh, parameters, W's, they kind of define the slope or the orientation of the plane. So this is a linear model, but this linear model is for the parameter A, and A is, of course, a part of the sigmoid function. And we drew the sigmoid function last time. It's like a sine function. It has a value of 1. So y is basically continuous value between 0 and 1. So 1 is the maximum possible value, 0 is the lowest possible value. And when a is 0, y is 0.5. 0.5 when a is equal to 0. And of course, which means that if a is greater than 0, meaning positive, it will have a value that is greater than 0.5 and leads towards 1. So when a tends towards infinity, you have a value of y which is tending towards 1. And when a tends towards minus infinity, you have a value of y that tends towards 0. And last time we also mentioned how we derived this function starting from the standard Bayes rule. And if you use the standard Bayes rule and derive this function, you find that A is actually the log odds, natural log odds, probability of C for binary classification, of course, given X divided by probability of uh, 1 X. So A is actually this. But of course, in logistic regression, we model this A as a linear function of some features. Okay? And obviously, from this Bayes rule and the value of A, you notice that when the ratio is a probability of C is equal to 1 divided by probability C is equal to 0 is greater than 1, this ratio is greater than, meaning that the probability of C is equal to 1 is higher, then the log of ln would be positive. If it is less than 1, then that would be negative. So that is relates perfectly to the sigmoid function interpretation of giving you a probability between 1 and 0 and having a value of 0.5 when a is equal to 0. Okay? So you notice that there is almost a direct relationship between logistic regression and naive Bayes. But in naive Bayes, you started off with the Bayes rule directly, and then you assumed a generative model for the data. And based on that generative model, you estimated those parameters and you got the posterior probabilities. While in logistic regression, you don't really worry about a generative model. You define features. Features are, you can say, values that are characteristics of text. We are dealing with text here primarily, and that are definitive with respect to the text classification problem that you are talking about. So we don't worry about it being a generative model. We worry more about in finding features that are discriminative for our particular task. So if I come back to my features, so features are what? X. So x1 to xm are features. So you can think of features as, for example, in general, a feature I, fi, is basically a mapping from D, which is your document, to a scalar value. In general, a scalar non-negative value in general. Of course, it can be negative, but usually it's always non-negative. So a feature is basically a mapping from a document. So in general, if you have something like this, F2D would give you X2 for that particular D. Okay? So with this more general definition, you can define anything that is relevant for your text classification problem as a feature. So this X could be a word, or this X could represent some characteristic or some value for a word. It could be something else as well. It could be, let's say, if it is a mixed text slash uh, image classification problem, it may include features for images as well. So in that sense, the logistic regression model is more, you can say, expressive, or in other words, it defines the features explicitly, not implicitly. So you can think of any feature that is relevant for your problem and include it in the linear model. So if we take these features to be words and their counts that occur in each document, then logistic regression becomes, I would say, identical to the naive Bayes or the multinomial naive Bayes classifier. Okay. So for different text classification problems, you can define different set of features in addition to words and their counts that appear in those documents. So let's just give you some quick example. Let's say you have the sentence segmentation problem. Although this is a more appropriately you can say, a sequence classification problem, which we'll talk about later on in this course. But here I'm talking about in terms of simple classification problem. So sentence classification would be, sentence segmentation problem would be what, for example? So after each word, maybe you define a window. So you have a sequence of words. I live in Lahore. Um, she lives in Islamabad. So we don't know exactly where a sentence ends, let's say, or we want to find out the boundaries of segments. So one way is to define a model where you take a sequence of words, and after the last word, you want to predict whether it defines the end of a sentence or not. So in other words, you have a binary classification problem defined after each word in the sequence. So, so for this, let's say you're taking 3 preceding words. Uh, so, so in this case, I live in. So is there a end of sentence after in, or live in Lahore? Is this an end of sentence? Or for example, in Lahore, she, and so on. So you have various binary uh, tasks that you would like to do. And of course, for this, you will have to have a training data set, which is labeled. But here I'm trying to explain the idea of features. So the features could simply be the words in the vocabulary that appear in those 3 words position, first, second, third. So maybe you can say X1 is the first word, X2 is the second word, X3 is the third word. But maybe this is not sufficient to find out whether that after the third word there is a uh, end of sentence concept or not. So you might want to include additional features. So for this problem, you can think of some additional features like what? So If we had punctuations, we could have included punctuations as well. But let's look at a feature, let's say X4, as if the next word is capitalized. So this feature X4 could capture what happens after X3. If if the next word after X3 is capitalized, so that could be a feature. Then this X4 would be 1 for this particular sentence, otherwise it will be 0. So this becomes a feature. You can also have other features as well. So for example, let's say X5 could be, so for example, X3 is actually a word, but you can say, is X3 the word in X3 all capitalized? So again, this is a binary feature. Why would this be important? Maybe this word is all capitalized, which means that it is an acronym. Like you're writing, for example, HEC, H a capital E, capital C, capital. So if it is an acronym, then there is less chance that after this you will have a full stop or end of sentence. Maybe the sentence is continuing. So you can have many such features defined for your particular problem. While if you had used the basic naive-based classifier, at least in the standard naive-based classifier, which is based on language modeling, you would only consider words and their occurrences in sequence. While in the logistic regression approach, features are explicitly defined, so you can think of out-of-the-box features that are appropriate for your particular problem. So you can also think of, for example, let's say spam filtering, another binary classification problem. You can take all the words within the email as features, but you can take additional features as well. For example, so you can have a feature, let's say X, whatever, let me give it a feature number 20. So is the sender in the block list? Of course, this is a very quick giveaway. If the sender is in the block list or spam list, then obviously this email is spam. So you can have other features as well, let's say X21. For example, the fraction of email written as all caps. So oftentimes, when you have spam email, just to avoid some very simple spam classifiers, the spammers would write all their email in caps. So that is also a quick giveaway. So fraction of email that is written in caps could be a feature. And what else? So you can have other features as well. So that's for spam filtering. So moving on to, let's say, sentiment classification. And let's say we are talking about the simplest sentiment classification, positive, negative sentiment classification. We want to identify whether a particular piece of text expresses a positive sentiment or a negative sentiment. So binary classification. So here again, you might think of features as either words, or in addition to words, you can define other features. So, so for example, so you can have features like so some feature like X. Let me just write N. So so for example, for emphasis, you can count or you can so you can so this feature could be number of X marks in the text. So, so this is a way of kind of quantifying the, you can say, uh, severity of the polarity. For example, it could, the author is like really excited about something in a positive sense or in negative sense. So this can be used as a feature. So if you talk about some other features, let's say you can have, for example, emoticons. Uh, so positive number of positive emoticons. Similarly, you can have another number of negative emoticons. So emoticons like smiley, that would be a positive emoticon. A frown would be a negative emoticon. So you can count those as well. So these typically are not words, but then you can always use them as features for your sentiment classification problem. All right. Uh, so so of, when we were discussing text pre-processing, we mentioned that we can, one of the pre-processing that you can do is change all text to lowercase. So sometimes in sentiment classification, that is not recommended because something that is written in uppercase uh, is often valuable clue for your sentiment classification problem. So someone who writes, let's say, amazing, and someone who writes amazing in all caps would have different emphasis. Someone who's writing in all caps is really excited or is trying to emphasize his point to a greater extent. So again, we would like to keep this distinction, and we would consider both of these words, let's say, separately or differently. Uh, Similarly, you can, for example, only if you want to simplify your problem, you can only use, for example, adjectives and nouns as features. So discard all other words. So usually these are the only words that are of importance for many simple sentiment classification problems. Adjectives are like excellent, great, good, bad, disappointing. So, so we can focus on these. Maybe you can add adverbs as well. So adverbs kind of qualify verbs and nouns. So, so thing like excessively good or terribly bad. So kind of emphasize your point. Uh, what else? So there's also the issue of negation. How do you handle negation? So oftentimes in your text, you will have something like not good at all. So if you consider simple unigram models or single words, so not would be a separate word, good would be a separate word, at all would be a separate word, all would be a separate word. So in other words, uh, we we have lost the information that not is kind of written in front of good, which is changing the meaning of good. So so one simple way of handling such situations is wherever you have a negation word, you create one token instead of two. You say not good as one token. So now this would be a different from, so this would be different from the token simply good. So good would mean the positive sense, not good would be mean the opposite sense. So you join in a way the token not and good. And sometimes some authors have said that if a negation occurs in a sentence, you should negate all words that appear after that negation. So for example, in the example above, instead of using not good at all as separate words, we will use these tokens, not good, not at, and not all until the end of the sentence. So we'll negate all the or have different tokens for all the words that occur after a given not or negation in a sentence. So it's kind of highlighting the fact that this not may impact all words that appear after this particular word. So this is something that can be done as well and has been tried. So by the way, these tricks, I'm just mentioning some of these tricks, or you can say ways of improving your model, but there might be others depending on the particular application. Uh, so one other thing, for example, so that's about negation. So far, or so far we had only talked about unigrams as features. So you can actually use higher order n-grams as features along with lower order n-grams features in a logistic regression model. So you're not restricted. Remember, in logistic regression, each you can define features almost at will. You don't have any restriction. We're not really worrying about it being a generative model. It's a discriminative model. We are focusing on the classification task. So maybe, for example, if you feel appropriate, you can have features. Let's say your vocabulary V is of size M, let's say. So in this case, you will have M unigram word, just not use word there, features. And then you can also maybe have bigrams features also included. So of course, there will be tons of bigrams from these M bigrams in general to the power of M. But let's say we select the most frequent from our training set and use those as a feature. So in addition to, let's say we also include M bigram features. So most frequent in training data. So now your feature set would then become 2M. So in addition to unigram, you also be using bigram. So for example, in the example I wrote before, I live in, or let's say, so not good at all. So your features would include the word not, the word good, the word all, at, the word all, as well as the bigram not good, the bigram good, at, and of course the bigram at all. So of course you will define the feature set before and then use it for a particular application. I'm just showing that for this data set, these features would have values while the other features would not have values, meaning that their value would either be zero if you're just counting those features. Okay. So you can have mixture of both unigrams, bigrams, trigrams as features for your text classification problem. All right. Any question? All right. So, continuing in this way, I mentioned previously the binary logistic regression. So the multi-class LR would have K models. So K class problem will have k models. So in other words, if I write the k as a superscript, I can write it in some other way as well, but let me write it as superscript k is equal to, and then of course we mentioned this last time, this is not the sigmoid function, this is the softmax function or the normalized exponential function of basically w. Um, so this k is for the parameter for the kth model, and then I'm also writing the transpose, and then of course x. Of course, the softmax function is, if you remember from the previous lecture, is not, you can say, just wk. It includes w1, 2, 3, 4 up till k. Okay? So it's not a function of just. So in other words, it's a coupled function. So if I write this again, the softmax function itself, so it is exp w k transpose x divided by, you have the sum for all k, okay, of exp w k transpose into x. So in the denominator, you have the exponent for all wkx, sum of the exp of all wkx. So in other words, for any particular yk, you need to have the values for all of those wk's. So in this way, this is, you can say this expression is coupled. It's not uncoupled from the other models. Okay? And we discussed last time why this is, because these yks would be probabilities that are properly normalized to a sum of 1. Okay. So by the way, what is yk? This is actually giving you the probability of c is equal to k given your x. And if you have multiple k's, you have multiple classes, then the best class would be the one that has the highest probability. Okay, so you have to choose the one with the max value. So let's say if you have k is equal to, let's say, 10 class problem. So how many parameters would you have in a multi-class logistic regression model? First of all, you have k models. For each model, how many parameters do you have? You have 1 plus m. Sorry. Yeah, 1 plus m. Let's say m are the number of features. Okay. So for one model, you have 1 plus m. 1 is w0 or w0, and m, of course, are the features. And then, of course, for k models, you will have k into m plus 1. So you will have multiple k's. So for example, if I write all those k's, w's separately, then I have so if I put all those w's as row vectors, so then basically what would I would have w basically so let me just say, okay, 1, 1, okay. Then you have w 1, 2, and w. Then how many features you have? Actually, 1 से नहीं शुरू होगा ये 0 होगा. ओके, ये वो दूसरा था, ठीक है, सही है. फीचर्स मैंने रो में रखने हैं, हाँ रो में रखने हैं, ठीक है. तो ये 1 ही कर देते हैं. ये 0 हो गया, ये 1 हो गया, and then we have the last one. 1n. So this is one for one model. Okay. And of course, you can put all those into a matrix. So the next row would be W2, 0, W2, 1, and so on. So you will have W2M. All of this could be put into a matrix. So you can call this your W matrix, capital W, matrix of weights. All right. Any questions? All right. So with this, I would like to move on to this basic neural network. So because a neural network is essentially a logistic regression model. So let's now introduce neural networks. Okay, before I go on, logistic regression is also oftentimes known as max entropy model. And this name is more common in the older days, especially in NLP or text analytics. So logistic regression and max entropy are essentially the same thing. So, but nowadays, of course, logistic regression, the name logistic regression is more widely accepted and known. And previously, especially in the NLP domain, logistic regression was called as max entropy classifier. Okay. Just to make sure you understand this, because you, in some literature, you will find this LR written as max entropy. Okay, now let's move on to the basic building blocks of neural networks. So a neural network, of course, as all of you know, were inspired from biological processing. The modern incarnations of neural networks, which are also oftentimes called as artificial neural networks, are more or less computational in nature. They have some aspect that were inspired by human computation, but of course, they have evolved and become more computation focused rather than being focused on kind of modeling the human processing system. So, but the origins, of course, are from the human processing system. Or you can say their intuition or motivation or inspiration is from the human processing system. Okay, so we'll start with talking with the feed-forward neural network. So of course, I wouldn't be able to give you an exhaustive historical perspective on neural networks. So that could be covered, let's say, in a machine learning course or even a neural network course, which I did teach several years back. Okay, so a feed-forward neural network is basically an architecture in which information flows in one direction, from input to output, through various processing units. So that's why it's called feed-forward neural network. And the basic building block of a neural network is the basic processing unit. or the simplest processing unit, which we will see is identical to a logistic regression model. So the processing unit is often drawn as a circle. So the output of that processing unit, let's say we are talking about a single circle, output is Y. Some activation function, we call this, let me say this is the function G, activation function G of the output of this processing unit is Y, and this output is computed as a function G of a scalar value. That scalar value is actually computed as the inner product of some vector W with another vector X. X is generally considered to be an input vector or the information vector, and W is a parameter vector. Okay? So X is the information vector at the start. We'll mention what is start and so on later on. At the start, this is actually your input. But let's say as your information flows through your network at some intermediate state, X can be some other vector that is transformed from the input vector. And similarly, at that particular stage, W is the parameter vector. So both of these are multiplied, W transpose X, or you can say W inner product X would give you a scalar. That scalar is then non-linearly, in general, non-linearly transformed by a function G. So this output would be the output of the processing unit. Okay? So let me just quickly draw this. So basically you have, this is the processing unit. This is the output Y. And then the input is basically several links, you can say. Each of those links has a weight. So W1 to, let's say, WM. And the information that flows through links is X1 to XM. So X1 multiplies with W1, X2 multiplies with W2, X3 multiplies with W3, XM multiplies with WM. All of them get summed up at that unit. So which is essentially the inner product between the vector W and the vector X. And then this unit has some nonlinear transformation, which we call as activation function or the transfer function. After that, you get the output Y. So this is the basic unit in a neural network. And as you can see, you have a nonlinear, in general, a nonlinear transformation being occurring. Actually, transformation may be linear, but the function is nonlinear. All right. So we'll come back to this function G later on. Now let me define the various stages of a feed-forward neural network. So these stages are often also called layers of processing. So we have input layer. This layer receives information from the outside world. So let's say this is the X of your text document that you want to process. Okay? You have input layers. And then after that, you have similar layers. Of course, there might be slight differences, but they are similar layers that are often in neural network terminology called hidden layers. layers. They could be many, one or more. And then after that, again, similar layer, but somewhat different. We'll mention that later on. We have the output layer. And after the output layer, you actually have the final Y, the final Y for the entire model. So far we have talked about a single unit. So each layer has multiple units and they're typically arranged in some order, usually as a row or a vector. Sometimes it could be 2D, but usually it's written, drawn as a vector, or row, or column. So, okay, coming before going to that, so we have a neural network which has information flowing from the left to the right. It goes through the first layer, which we typically call the input layer. Then it goes through multiple layers we typically call hidden layers. Why are they called hidden? Because they're hidden from the outside world. And then finally it goes through the output layer to the output outside. So at start you have X, in general, X as input, and after that you have Y as output. Okay. So such a neural network is typically called, so basically neural networks are often defined, feedforward neural network, by the number of layers. So for example, in this particular case, let's say you have input, two hidden layer, and then output. So this is basically called a 3-layer network. So we do not count, you can say the input layer, or you can even say the output layer, but usually the input layer. So we subtract one layer and say this is a 3-layer neural network. So 2 hidden layers and 1 output layer. Okay. So if there is a 6-layer neural network, then it will have 5 hidden layers and 1 output layer. When if there's a 2-layer neural network, it has 1 hidden layer and 1 output layer. If it is a 1-layer neural network, it simply has the output layer. So the input directly goes to the output. Okay. Okay. So now let's define the parameters and how information flows through a feed-forward neural network. So we had talked about a single unit before. So now we'll expand it to a full feed-forward neural network. Okay. So let's say we have input X. X is a vector of length M, let's say. Okay. So X is a vector of length N. Okay. So which means that the input layer would have M inputs. Okay. Each input is each element of this vector X. So each of these input would then be multiplied with a corresponding weight. But before that, let's look at the hidden layer. Let's say we have one hidden layer, and let's say this hidden layer, this is the first hidden layer. It has N, let's say 1 units. It's not just now a single unit, it's a layer. It has N1 units. You can say you are drawn them as a column, one after the other. And then let's say you have an output layer. Let's say this is again a single unit. Okay? And of course, single unit outputs just a scalar y. Okay? So let's consider this simple neural network and consider the information flow through this network. So if I'm able to draw this, let's see. So if I'm able to draw this, let's see. So you have, this is the hidden layer I'm going to draw. So you have multiple units now here. How many units? N1 units. This is my hidden layer. And then you have the output layer here, which is a single unit, which gives you your Y. And then for each hidden unit, again, I kind of difficult. So we have inputs here. These are not only inputs, these are not units. So how many inputs? X1 to Xm. So all this X1 to Xm would be inputted to each of the hidden layer. Okay? And of course, the hidden layer की जो output है, that would be of size N1. All of those would go to the next layer, which is of a single unit. So let's see, kind of here, okay. I mean, draw it again. Or let me move to the previous slide. So if I talk about one unit in the hidden layer, so this has inputs coming in from all the M inputs, X1 to Xm. And of course, each of these links would have their corresponding weights. Similarly, एक और unit है hidden का, उसमें भी सारे इन्हीं M से आपके पास inputs आ रही हैं, and they will have their corresponding weights. And similarly, जब output में जाएंगे तो इन दोनों से information जाएगी to a output layer. So information flows from left to right through weights and through processing units. And those processing units are arranged in layers. All right, so now let's do the processing. So input is X, the vector of size M. So we will have a matrix of weights from the inputs to the first hidden layer. So we will call this matrix, let's say W, superscript, let's say 1, which is just indicating, or let me just use underscore. Notations might be different in different books, underscore 1. So this is the weight matrix from inputs to first layer. Okay? So what would be the size of this? The size of this would be the size of the hidden layer, which is of course the columns. And then the size of this would be, let me write it here. So W1, 1 would be of size M into N1, meaning M is the number of inputs and N1 is the number of layers at the hidden layer. So the processing now can be simply written as, so let's say I say the output at the first hidden layer is Y1. So this is now simply some function G. This function, by the way, can be different from that other function, but let me write it G as before. G, then I have W, which is 1 matrix multiplied by X. So W matrix is of size M. Okay, this is not multiplying properly. X1. इसी तरह I think बेहतर रहेगा, so उसकी size change कर लेते हैं. So because X is of size M, so I call this N1 into M. ठीक है? So now this would multiply and give you a column vector which is equal to the size n1. So जो W matrix है उसके कितने columns हैं? उसके m columns. Those m columns will multiply with m of the vector x to give you one value. So this is the output of the first unit in the hidden layer. The second row would multiply with the vector x to give you the output of the second unit, and so on. And of course, output would be after applying g. So this g is applied to each element of this vector separately. Remember, wx would give you a vector of size n1. Okay? And g is applied to each element separately. ठीक है? So ये आपके पास अब output आ गई hidden layer की. अब final output, let's say I call that y2, ठीक है, would now be some function, let me give it a different name, f, of another weight matrix w2 into y1. ठीक है? So now this would give you the output of the final layer. And if you had multiple layers, this process would be repeated at each layer from one layer to the next layer. So in this example that I said output has just one unit. So W is actually just a vector, because A ki jab, it's not really a matrix, it's just one row vector, because there are not many inputs. And so they're not, there's only one output unit, so it just has one weight vector associated with that unit. So it's just a vector. So that vector multiplied with y1 would give you a scalar. That scalar is then modified with f to give you the output y2. So essentially, this is a feed-forward neural network. So in this particular case, where two-layer neural network, you had two weight matrices, W1, W2. W1 corresponded to the first hidden layer, and then of course W2 to the second, and up to whatever is the output layer. And the size of W would be the number of units in the hidden layer multiplied by the number of inputs coming from the preceding layer. Okay. For example, if you talk about W1, inputs coming from the preceding layer was the input to the network itself, which was M, and the number of hidden layers was N1. Okay. Actually, you can continue this notation. Output, इस case में जो output layer है, which has a single unit, so N2, वही notation use करें, would be 1. ठीक है. Okay. So the parameters of this model are, of course, the weight matrices. So W, I are the parameters of the, you can say, feed-forward neural network. Okay? And in general, as we saw for logistic regression, usually we will have an additional input at each layer, which is fixed at 1. Remember, in the logistic regression, what did we do? W naught plus W1 into X1. Okay? So you can think of this as W naught X naught zero plus W1 X1 plus so on, where X naught is equal to 1. It's fixed at 1. Okay? So if you, each layer, we do assume that there is an additional input and a corresponding weight. That additional input is fixed, is not changeable, it's equal to 1. And of course, its weight parameter is adaptable, is W naught. So in that case, of course, in the previous calculation, appropriately the sizes of x and w would change with one more value. ठीक है? So now let's look at the functions. I talked about two functions. I said there's a function f, which let's say, and in general, both functions are considered or usually used to be nonlinear functions. F and g, these are two functions. So g, you can say, is used for hidden layers, and f is used for output layer. Okay? Let's say, I mean, I'm just giving you the difference between the two. So what are the functions that are commonly used for G? So G may, the common functions that are used are, of course, the sigmoid, which is the function that you saw for the binary logistic regression. Okay? Sometimes we also use the tangent hyperbolic, and I'll mention this shortly. And more recently, we also use an even simpler function, which we call the rectified linear unit, or sometimes just abbreviated RELU. Okay? And as I said, these functions are nonlinear, meaning that there is nonlinearity in those functions. So we have already seen the sigmoid function. This is a continuous function which varies from 0 to 1, like an S. Okay? So tangent hyperbolic has the same shape as the sigmoid. So tangent hyperbolic of H, let's say, it basically ranges between -1 and 1. So unlike the sigmoid, which ranges from 0 and 1, this ranges from -1 to 1. And when a is equal to 0, it has a value of 0. While in the sigmoid, when a is equal to 0, it has a value of 0.5. So shape बिल्कुल exactly वही है S function. But इसके, it has a negative value, it has a positive value. ठीक है? So for the hidden layers, it has been found that this function does slightly better. Of course, in modern days, when you have tons and tons of data and lots of training examples, तो बहुत ज़्यादा फर्क नजर नहीं आता. But from a theoretical perspective, this is better because it gives you a negative value also. It allows the neural network to arrange or adapt in a better way. Okay? So this is the tangent hyperbolic, which is slightly preferred, you can say, with respect to the sigmoid for the hidden layers. And then we have the RELU, rectified linear unit. So rectified linear unit gives you a value in 0 and 1. Of course, you can change it to -1 and 1 as well. But इसकी जो shape है वो मैं draw करता हूँ. It's not smooth, but it's still non-linear. Okay. इस पे कुछ बना होगा. All right, I hope this page has cleared up. So rectified linear unit का very simple function है. ये 0 है और फिर ये straight ऊपर जा रहा है with a slope of 1. So, and this change usually occurs at a is equal to 0. Okay? So it's linear after 0 when a is greater than 0, and it's 0 when a is less than 0. And of course, इसको थोड़ा सा कई दफा change भी कर लेते हैं कि negative value भी दे. But usually, as I said, इतना ज़्यादा फर्क नहीं डालता मॉडर्न डे डीप लर्निंग मॉडल्स में. So it has, if you compare this with the sigmoid or tangent hyperbolic, वो limit हो जाते थे at the extremes. While the rectified unit only limits itself at the lower value, upper value पे limit नहीं होता, it has a continuously increasing value. ठीक है? So if I write this in equation form, A, so this is equal to 0 when A is less than 0. ठीक है? Yes, A is less than 0. And then it is equal to A when, yeah, simply A otherwise. ठीक है? Linear है ना? Output is simply A when A is greater than 0, and output is 0 rectified when A is less than 0. So this actually RELU, rectified linear unit, was proposed or has become popular more recently, I would say in the last 10 years maximum. And it is quite commonly used in deep neural networks. And one of the key motivation factors for this is that it is computationally more efficient than the other, because those are more complex functions involving exponential. And of course, the tangent hyperbolic. And we will discuss some other properties of these things later on, and some of the issues that arises. We'll discuss that later on. Okay, finally, the output layer, F. So the output layer would depend on your problem. So F would be sigmoid, and of course a single unit if you're doing binary classification. ठीक है? F would be the softmax, which is of course is a coupled function. It's not really an independent function. If you are using multi-class classification. And of course, F could be simply linear if you're doing regression. Of course, we don't focus too much on regression in this course, but if F is linear, then you can use a neural network, a feedforward neural network, for solving a regression problem. ठीक है? ठीक है? So this kind of briefly discusses the activation functions that are used in a neural network. In the hidden layer, we have sigmoid, tangent hyperbolic, or the rectified linear unit. At the output layer, it is dictated by your particular problem. For binary, where you typically would have one unit, at the output layer, you use the sigmoid function or logistic function. And if you have a multi-class classification problem, let's say a K-class classification problem, you'll have K units at the output layer. And all those units will be processed according to the softmax function. This is coupled, as I said. You need information from the others as well. And then if it is a regression problem, and of course, regression can have multiple units if it is a multi-regression problem. But each of those processing units would be linear. This function F would be linear. So, okay, I think we're almost running out of time. So essentially, this is a feed-forward neural network that can be used to solve classification problems. And in the case of text classification, you can solve all text classification problems using a feed-forward neural network, sentiment classification, sentence boundary classification problem, and for example, topic classification and so on, spam filtering and so on. So I think I will probably stop here. So in the next class, I'll start with a brief comparison of these, and then we move on to vectors and embeddings, and which is more relevant to NLP. Most of the last two lectures was a kind of refresher of machine learning. But I'm not too sure. Next lecture में मैं नया content शुरू करूँ या do it a review lecture? एक lecture मैंने makeup भी करना है. I missed one lecture earlier on. So if you guys are really going to participate in a review, तो मैं review कर लूँगा. Otherwise, we can continue with the content. ठीक है. तो review कर लेंगे. ठीक है. चलें ठीक है. I think some of you are more interested in reviews, so we will do a review session. But for the review session, what I will do is एक तो खैर content के ऊपर मैं over I will go over the content that we actually covered in the course point in a high level fashion, and which would also become your syllabus for your midterm exam. And if you have specific questions, please come prepared for asking those questions. ठीक है. And if you don't have enough questions, we might end before 11:15. The syllabus for the midterm is essentially everything that we covered till today. So I will send out an email as well, but जो regularly lectures को पढ़ रहे हैं या सुन रहे हैं तो वो उनको पता है everything that is covered till today would be part or tested in the midterm exam.